All right, now we want to allow for a little bit, we want to allow ourselves to take not just monotone transformations, because sometimes we want to study more general functions of random variables. So we cover that under what's called a many-to-one transformation. So in a many-to-one transformation, there are many potential values, more than one value of x that can go to the same value of y. So let's see what we mean by that. Let's take an example. Let's suppose that x standard normal 0, 1, and so it has a density which is 1 over square root 2 pi e to the minus x squared over 2. And that's for all real numbers. And let's define y to be x squared. Well, x squared is not many to one. Or no, I'm sorry. X squared is not 1 to 1. X squared is many to 1 because the same value. So plus and minus x both get to map to the same value, x squared. Okay. So this is the distribution of y is what's called the chi-squared distribution. With 1 degree of freedom. So what can we say about the density? Well, we don't have a change of variables formula for the density just yet, because what we previously were able to do was just in the case of a monotone transformation, and this is not a monotone transformation. But we can still actually do this by working through the distribution function. So again, just because we don't have a theorem that directly applies to the situation we're in doesn't mean that we can't work with it. A distribution is determined by its distribution function. So we just work from that definition. Well, what's the probability that y is less than or equal to little y? Well, it's the probability that x squared is less than or equal to little y by definition. So now we have something in terms of probabilities for the random variable x. And when is x squared less than or equal to y? Well, this happens as long as x is between minus square root of y and plus square root of y. Which in terms of the distribution function of x we can express in this way. And we get the density then by taking the derivative of the distribution function. So it's the first derivative of the distribution function, which in this case is two over two square root of y, density of a standard normal evaluated at square root of y. So we put this in, we get 1 over 2 pi square root 1 over square root 2 pi y e to the minus y over 2. And y has to be positive because y is the square of x. Notice by looking at this, this is also equivalent to the gamma density with parameters 1/2, 1/2. Okay, so the chi-square distribution with 1 degree of freedom is the gamma 1/2, 1/2. Okay. Okay, so that's how we would deal with the many-to-one transformation. Is we work directly from the definition and then the distribution function. Some additional facts about transformations that we want to record here. Number one, suppose f is monotonically increasing CDF of a random variable x. So CDFs don't have to be monotone increasing. They can have flat parts, right? If there's no probability between a certain partial. Let's assume that f is monotone increasing. Then if we define a new random variable, we use f as our, we're going to use f as our transformation. Okay. We use f as our transformation. And what we get then is that if we transform x through f, what we get back is a uniform 0, 1. So the proof of this is that the probability, the distribution function of z being less than or equal to u has to equal u, right, in order for this to be true, because that's the distribution function of the uniform. Well, by definition, z is f of x. And we've assumed that f is invertible because it's monotone increasing. But now this is the probability that x is less than or equal to some value, which is the distribution function of x evaluated at the value, f inverse. Well, f and f inverse cancel. And we get u. This is the CDF of the uniform. And now let's consider the alternative. Let's let u be a uniform. 0, 1. Then define x to be f inverse of u, where, again, f is the distribution function of some random variable called x, right? This random variable will have CDF f. So how do we work through that? Well, we want probability x is less than or equal to x. Well, x is defined as f inverse of u. F is invertible, so we can get rid of, we can move it from left to right. But now this is the distribution, this is the probability that a uniform random variable is less than something, which is just f of x. So then the CDF of x is F. Okay, so this turns out to be, these two facts turn out to be extremely important in simulation. And we're going to come back to show how these two theorems on their own are really behind all of the statistics, really one of the most fundamental aspects of statistical application, which is being able to simulate random variables.